A tiny spacecraft built in the 1970s is now navigating the space between stars. This is the story of Voyager, humanity's most distant emissary, on a journey beyond the edge of our solar system. By the end of this video, you will understand the untold secrets of its epic mission and the profound discoveries still echoing back to Earth. We will uncover how this probe overcame impossible challenges and what its faint signals from the void reveal about our cosmic neighborhood. How far can human curiosity truly reach? This grand celestial alignment presented a fleeting chance, a door that would not open again for another 175 years. A spacecraft launched in the late 1970s could use the gravity of one giant planet to swing itself toward the next, a cosmic pinball game orchestrated with breathtaking precision. Scientists called this the Grand Tour, and it was the most ambitious journey ever conceived. The vision was to send a single emissary across the solar system to reveal the secrets of worlds that were, until then, only faint points of light in our telescopes. But ambition alone was not enough. The political and financial hurdles were as vast as the journey itself. NASA had to convince Congress to fund a mission that would take over a decade just to complete its primary planetary flybys, a tough sell in an era of tightening budgets. The engineers faced a seemingly impossible task. They needed to build a spacecraft robust enough to survive for decades in the harsh environment of deep space, yet smart enough to perform complex maneuvers on its own, millions of miles from any help. Its computer had less memory than a modern car key fob, yet it had to navigate the solar system. Its cameras had to capture clear images while moving at tens of thousands of miles per hour. Every component, from its nuclear power source to its thruster jets, had to be perfected, tested, and built to last. This was not just about building a probe, it was about building a legacy. The sheer audacity of the plan set the stage for a mission that would ultimately redefine our place in the cosmos. The result was a masterpiece of engineering, a 10-sided central body called a bus that housed the spacecraft's electronic heart. This geometric core was packed with the most advanced computer systems of the era, along with fuel tanks and a carefully chosen suite of scientific instruments. From this central hub, a massive parabolic dish antenna, 3.7 meters across, reached out like a giant ear, its sole purpose to listen for whispers of command from Earth and to send its own precious data back across the unimaginable void. But what tools would this distant traveler need to unveil the secrets of alien worlds? It carried cameras to capture landscapes no human eye had ever seen, spectrometers to dissect the very light of distant atmospheres and reveal their composition, and sensitive magnetometers to feel for the invisible magnetic fields of giant planets. Perhaps most critically, it held plasma detectors, instruments designed to sense the solar wind, that relentless stream of charged particles flowing from the sun. Yet all of this sophisticated machinery required a reliable power source, something that could not rely on the distant sun's fading light. The solution was both elegant and potent: 3 nuclear batteries known as radioisotope thermoelectric generators. These RTGs performed a simple but profound alchemy. They took the steady, relentless heat given off by the natural decay of plutonium-238 and converted it directly into electricity. This robust and sophisticated design was not just for a quick tour of the inner solar system. It was built for the long and perilous journey ahead, a testament to human ingenuity meant to function long after it left the familiar planetary system behind. Yet the Voyager spacecraft carried more than just scientific instruments. It held a message, Attached to each probe's side is a 12-inch gold-plated copper disc, a time capsule for the cosmos known as the Golden Record. This was not a tool for studying planets, but a profound gesture aimed at a future and far more distant audience, any intelligent being that might one day intercept this silent traveler. Its creation was led by the visionary astronomer Carl Sagan, who assembled a team to answer an almost impossible question. If you could only send one small sample of Earth into the void, what would you include? The result is a stunning portrait of our world. Etched onto the disk's grooves are the sounds of a living planet, from the haunting songs of humpback whales to the rumble of thunder and the gentle patter of rain. There are greetings spoken in 55 different human languages, offering hellos from every corner of the globe. The musical selections are a symphony of human creativity, spanning cultures and centuries, from Bach and Beethoven to Chuck Berry and traditional melodies from across the world. The record also contains 115 images encoded in analog form, depicting everything from mathematical diagrams and human anatomy to scenes of daily life, our cities, and our natural wonders. But how would an alien entity with senses and technology completely unknown to us ever decipher this gift? The record's cover provides the key. It is engraved with symbolic instructions, using the most universal language we know, science. A diagram shows the hyperfine transition of neutral hydrogen, the fundamental clock of the universe, to define the record's playback time. Another illustration provides a map locating our solar system relative to 14 pulsars, the rapidly spinning corpses of dead stars that emit incredibly regular radio beams. These cosmic lighthouses pinpoint the spacecraft's origin in both space and time. The Golden Record is more than a scientific experiment. It is a message in a bottle cast into the vast cosmic ocean. It is a testament to a species brave enough to reach out, to say we are here, and to offer a hand of friendship to the great unknown. Two ambassadors launched from Cape Canaveral just weeks apart, Voyager 2 first on August 20, 1977, and Voyager 1 following on September 5. They rode atop Titan 3 Centaur rockets, the most powerful available. Each launch a controlled explosion of fire and thunder that pushed against Earth's gravity. The timing was not arbitrary, it was everything. This was the only window, the single moment in a human lifetime when the planets were arranged in just the right way. A successful launch now meant a slingshot journey across the solar system. A failure meant waiting for more than a century and a half for another chance. The world watched, holding its collective breath as these twin explorers began their ascent. There was no room for error. The rockets had to perform flawlessly, and they did. Each spacecraft was flung onto a perfect trajectory, a path that would first use the immense gravity of Jupiter, not just as a destination, but as a celestial slingshot. This gravity assist was the mission's secret weapon, a way to steal a little energy from the planet itself, whipping the probes around it and firing them onward toward Saturn at incredible speed. This successful departure was more than just a technical triumph. It was the first, most critical step into a profound and uncertain darkness. With those fiery departures, a decades-long conversation with the void had officially begun. The first destination was a world of colossal scale, a giant waiting in the dark. When Voyager 1 finally reached Jupiter in March of 1979, it did not find the placid, banded sphere seen from Earth. It revealed a dynamic and chaotic realm, a world in constant, violent motion. The first breathtaking images showed the Great Red Spot not as a faint smudge, but as a churning, Earth-sized hurricane, a storm that has raged for centuries. Swirling cloud bands in shades of cream, orange, and brown striped the planet, each one a fast-moving river of gas thousands of miles wide. The sheer energy of this turbulent atmosphere was staggering, a place where winds scream at speeds exceeding 400 miles per hour. But Jupiter itself was only half the story. The planet's moons, once thought to be inert balls of rock and ice, turned out to be worlds of their own. The most stunning discovery was on Io. Voyager's cameras captured plumes of material shooting hundreds of miles into space from its mottled yellow surface. This was not impact cratering or geological settling. This was active volcanism, the first ever seen anywhere beyond Earth. Io was the most volcanically active body in the entire solar system, its interior constantly churned and heated by the immense gravitational tug-of-war between Jupiter and its other large moons. The probe also made a completely unexpected find, a faint, dusty ring encircling the giant planet. This thin band of debris, invisible from Earth, showed that ring systems might be more common than anyone had dreamed. Every piece of data sent back was a revolution. Jupiter was not a quiet, static giant, but a complex, storm-racked system with a powerful magnetic field and a collection of bizarre, active moons. This triumphant encounter was a validation of the entire audacious mission, proving that the Voyagers could not only survive the journey, but completely rewrite the textbooks. The success at Jupiter filled scientists with a thrilling anticipation for what lay ahead at the next stop, the enigmatic ringed planet Saturn. The journey from Jupiter was a high-speed race toward an even more mysterious destination. When Voyager 1 arrived at Saturn in November of 1980, it revealed a system of almost impossible elegance. The planet's famous rings, which from Earth appeared as a few solid bands, were now seen in their true glory. They were not simple solid hoops, but a vast, complex disk of countless individual ringlets, like the grooves on a cosmic record. These rings were made of trillions of swirling ice particles, each one a tiny moon in its own right, ranging in size from specks of dust to chunks as large as a house. This was not a static structure, but a dynamic and intricate dance of gravity and motion. Yet the rings were only the opening act. The mission's planners faced a critical choice at Saturn, a single decision that would dictate the ultimate fate of each Voyager. The primary target was Triton, Saturn's largest moon. Previous observations had hinted it might have an atmosphere, and Voyager's close look confirmed it in spectacular fashion. Triton was shrouded in a thick, unbroken orange haze, a dense gaseous envelope unlike anything found on any other moon. This was a world with its own weather, its own chemistry, a place that might even have lakes of liquid methane on its hidden surface. The discovery was so compelling that it dictated Voyager 1's final maneuver. To get a better look, the probe used Saturn's gravity to sling itself on a path sharply upward, out of the flat plane of the solar system, sacrificing any future planetary encounters for this one profound glimpse. As Voyager 1 angled away and Voyager 2 later continued its own tour, other strange moons came into focus. There was Mimas, a small world dominated by a crater so massive it looked like the Death Star from science fiction films, an impact that nearly shattered the moon. Then there was Enceladus, a brilliant, white orb with a surface as smooth as a billiard ball in some regions, suggesting something had erased its ancient scars. This smoothness was a tantalizing clue, a hint that Enceladus might not be entirely frozen solid. Perhaps some internal heat was reshaping its face, a secret that would remain locked away for decades. These encounters did more than just catalog new worlds. They transformed Saturn from a distant, ringed beauty into a complex planetary system full of individual characters and unanswered questions. With its work done, Voyager 1 began its long climb, its cameras turning back for one last, iconic look at home before venturing into the infinite dark. That critical decision at Saturn was a moment of profound scientific sacrifice. Mission controllers were faced with a cosmic fork in the road for Voyager 1. One path used the planet's gravity to slingshot the probe upward, out of the flat plane where all the planets orbit, in order to get an intimate look at the mysterious moon Triton. The other path would have bent its trajectory to stay within the ecliptic, setting up potential flybys of the ice giants Uranus and Neptune. The scientific pull of Triton was irresistible. It was the only moon known to have a substantial atmosphere, a thick orange shroud that might hide a landscape of alien organic chemistry. Choosing to study it meant Voyager 1's planetary mission was effectively over, its grand tour cut short. But it also meant securing a close-up view of a world that could hold clues to the early Earth. The gamble was immense. This decision placed the entire burden of reaching Uranus and Neptune onto Voyager 2, a spacecraft already years into its journey and millions of miles away. Its systems were aging, its components subjected to years of cosmic radiation and extreme temperatures. Could this single probe, now alone on the most ambitious leg of the journey, survive long enough to complete the tour? The fate of exploring the outer solar system now rested on one set of aging electronics and the team on Earth who had to guide it there. With Voyager 1 angling up and out of the solar system, Voyager 2 was now utterly alone, carrying the full weight of humanity's grand tour on its aging shoulders. Its new path was a lonely arc through the dark, a multi-year cruise toward the ice giants Uranus and Neptune. The distances involved were staggering. By the time it reached Uranus, the signal from Earth, traveling at the speed of light, would take over 2.5 hours just to reach the probe, and another 2.5 hours for a reply to come back. A single round-trip communication took more than 5 hours, making real-time control impossible. Every command had to be perfect, uploaded days or weeks in advance. The spacecraft itself was changing, its nuclear batteries producing less power with each passing year. Mission engineers performed a kind of remote triage, carefully deciding which non-essential systems to turn off forever to conserve every precious watt for the core scientific instruments. They uploaded new software across the immense gulf, teaching the probe new tricks to compensate for its aging hardware. This was not just a mission of exploration, it was a masterclass in remote medicine for a patient millions of miles away. The long, silent coast between planets was a test of patience, with the ground team constantly listening for the probe's faint heartbeat, a signal that grew weaker with every million miles it traveled. Each successful check-in was a small victory, a confirmation that human ingenuity was still holding sway in the void. This extended solo mission pushed the boundaries of what was thought possible, demonstrating not just the incredible durability of the Voyager design, but the profound dedication of the team on Earth. They were shepherding a machine into utterly uncharted territory, further than any human-made object had ever gone before. As Voyager 2 finally approached Uranus in January of 1986, it revealed a world that defied all expectation. The planet was not merely tilted, it was lying on its side, rolling around the sun like a cosmic ball. This strange orientation meant that for a quarter of its 84-year orbit, one pole is in constant daylight while the other is locked in an endless, frigid night, each season a staggering 21 years long. The planet's pale blue-green face, colored by methane in its upper atmosphere, appeared deceptively calm, a stark contrast to the stormy giants Jupiter and Saturn. But this serenity hid profound mysteries. Voyager 2's instruments pierced the veil, discovering 10 entirely new moons and 2 faint, dark rings that had been completely invisible from Earth. These findings alone would have made the encounter a triumph, but the most bizarre discovery was yet to come. the probe's magnetometer detected a magnetic field that was utterly unlike any other. It was not centered on the planet's core, but was skewed dramatically to one side, as if the planet's internal compass had been broken. This lopsided magnetic field suggested that deep within Uranus, the processes that generate planetary magnetism were happening in a layer of slushy, electrically conductive ice, not in a molten metal core. This was the key evidence that confirmed Uranus as the first true ice giant, a world composed mostly of fluids like water, ammonia, and methane ices under immense pressure and heat. This single flyby transformed our understanding of planetary diversity, proving that not all giant planets are built the same. The lonely probe had unveiled a world of strange geometry and hidden forces, a crucial data point in the puzzle of how solar systems form, before it continued its relentless journey into the black, racing toward its final planetary rendezvous. 3 years later, in the deep freeze of 1989, Voyager 2 finally approached its last port of call. Neptune hung in the void like a perfect sapphire, a world so distant it receives only a fraction of the sunlight that warms Earth. Logic suggested it should be a quiet, frozen ball, its atmosphere slowed to a crawl by the cold. The reality was a breathtaking shock. Neptune was a maelstrom. The probe's instruments clocked winds screaming at over 1,200 miles per hour, the fastest ever recorded in our solar system. These were not gentle breezes, but supersonic jets of gas tearing across the planet's blue methanescape. Then came the discovery of the Great Dark Spot, a colossal Earth-sized hurricane raging in Neptune's southern hemisphere, a twin to Jupiter's famous storm, but even more powerful and fleeting. How could a planet so far from the sun's warmth muster such violent energy? The answer lies deep within Neptune itself, which radiates more than twice the heat it absorbs from the sun. This internal furnace, the leftover heat from its violent formation billions of years ago, drives the chaotic weather, proving that a world does not need to be close to the sun to be fiercely alive. But Neptune itself was only half the final act. Its largest moon, Triton, awaited. Triton was an enigma from the start, orbiting backwards relative to Neptune's spin, a clue that it was likely a captured wanderer from the Kuiper belt. As Voyager 2 drew near, it revealed a landscape that defied all expectation. The moon was a fractured mosaic of icy cantaloupe terrain and smooth frozen plains, but the most astonishing sight was active geyser-like plumes of dark material shooting 5 miles into its thin, wispy atmosphere. These were nitrogen geysers erupting from beneath a surface that is only 38 degrees above absolute zero, the coldest measured world in the solar system. The faint heat of the distant sun, or perhaps the squeeze of Neptune's immense gravity, was enough to power these cryovolcanoes on a world that should have been geologically dead for eons. This final, triumphant flyby was the capstone of the Grand Tour. In a single 12-year journey, 2 small spacecraft had unveiled the 4 giant planets in all their splendor and strangeness, forever rewriting our understanding of the solar system's outer realms. With its primary mission complete beyond anyone's wildest dreams, Voyager 2 now joined its twin in a new and even more profound phase of the journey, turning its sensors toward the true final frontier, the empty, windless sea of interstellar space. The planetary tour was over, but the true nature of the Voyager's journey was just beginning. Their new mission was to map the very edges of the Sun's kingdom, a vast and invisible structure known as the Heliosphere. Imagine the Sun constantly exhaling a stream of charged particles, a 1,000,000-mile-per-hour gale called the solar wind. This wind blows outward in all directions, carving out a protective bubble within the galaxy, a cosmic shield against the harsh environment of interstellar space. Outside this bubble, the Milky Way is flooded with galactic cosmic rays, high-energy particles accelerated by distant supernova explosions. The heliosphere acts like a planetary force field on a stellar scale, deflecting the majority of this dangerous radiation and creating a relatively calm harbor for our solar system. For the first time, humanity had sent instruments to directly probe this mysterious frontier. The Voyagers became our remote sensors, their aging instruments meticulously tracking the strength of the solar wind, the direction of the sun's magnetic field, and the increasing drumbeat of cosmic rays from the galaxy beyond. This was not a quick flyby, it was a slow, decades-long immersion into a region no spacecraft had ever reached. Their survival was paramount, a testament to the engineers who built them to last. Every day they traveled further was a new record, every date a point a revelation, painting the first real-time map of our solar system's final protective layer. This long-term study transformed our understanding of the sun's influence, revealing that the edge of our cosmic neighborhood is not a hard wall, but a dynamic and ever-changing boundary, a place of constant negotiation between the star we call home and the vast ocean of the galaxy. The first tangible boundary in that interstellar sea was a place of profound transition, a frontier known as the termination shock. For decades, the solar wind had raced outward from the sun at over 1 million miles per hour, a supersonic river flowing into the void. The termination shock is the invisible line where this wind abruptly slams into the pressure of the interstellar medium, the thin gas and dust that fills the space between stars. It is the point where the solar wind, like a wave hitting the shore, is forced to slow down, piling up and becoming denser and hotter. The Voyagers were our first ships to cross this cosmic shoreline. Voyager 1 reached it first in 2004, followed by its twin in 2007. The fact that they crossed at vastly different distances from the Sun was a revelation in itself. Voyager 1 encountered the boundary about 8.7 billion miles out, while Voyager 2 found it nearly 1 billion miles closer in. This single observation shattered the idea of a perfectly round heliosphere. Instead, the data painted a picture of a squashed and lopsided bubble, as if some immense pressure from the galaxy is pushing in on one side, distorting the sun's protective envelope into an asymmetrical shape. The instruments recorded the moment of crossing in exquisite detail. The particles of the solar wind, once moving at breathtaking speed, suddenly crashed into a wall of interstellar material, their energy converting into intense heat. This was not a gentle slowing, but a violent, turbulent collision zone. The discovery of this asymmetry and the dramatic physics at the shock were crucial pieces of the puzzle, allowing scientists to build more accurate models of our solar system's final protective layer. It was the first hard evidence of the complex forces shaping our place in the galaxy, a milestone that proved the Voyagers were truly entering a new realm, one governed not by the sun alone, but by the vast ocean of the Milky Way. Past the termination shock, the solar wind does not simply vanish. It enters a strange and turbulent buffer zone called the Heliosheath. This is the outer layer of the sun's protective bubble, a region of compressed and superheated particles caught between the push of the solar wind and the immense pressure of the galaxy. Imagine a vast, slow-moving river suddenly meeting the open ocean, its waters piling up into a chaotic, churning estuary. That is the Heliosheath. Here, the million-mile-per-hour solar wind is abruptly forced to slow to a relative crawl, condensing into a dense, hot plasma. The sun's magnetic field, which once streamed outward in orderly lines, becomes tangled and amplified, wrapping around itself in a complex web of energy. The Voyagers drifted through this region for years, their instruments measuring a complex soup of particles. They revealed a delicate and dynamic balance, where the inward pressure from the interstellar wind precisely countered the outward push of our own solar wind. This entire region acts as a final filter, a cosmic shock absorber that slows and diverts the solar material, preparing it to eventually merge with the galactic environment. Studying the Heliosheath was like learning the physics of a stellar coastline, providing crucial insights into how all stars interact with the space between them. Every new data point from this turbulent zone brought the Voyagers closer to their ultimate goal, the final and most profound boundary of all, the edge of our solar system. The heliopause was the ultimate finish line, the final curtain between our solar system and the true galaxy beyond. This is the boundary where the pressure of the solar wind finally equals the pressure of the interstellar wind, a delicate balance point that marks the true edge of the sun's influence. For years, the Voyager team watched their data, waiting for the signs. Then, in August of 2012, the instruments on Voyager 1 spoke a clear and historic truth. The number of charged particles from our sun plummeted to nearly zero, as if a great wind had suddenly ceased to blow. At the same instant, the probe was bombarded by a flood of galactic cosmic rays, high-energy particles from distant supernovas and stellar explosions. The change was sharp and decisive. After 35 years of travel, Voyager 1 had officially pierced the heliopause. It was no longer within the sun's protective bubble. It was adrift in the interstellar medium, the first human-made object to enter the space between the stars. The confirmation from Voyager 2 6 years later was equally profound. Its different and still functioning suite of instruments provided a second, richer data set, proving the first crossing was not a fluke and revealing that the boundary itself is a complex, multi-layered structure. This was not just a scientific milestone, it was a moment of profound symbolism for our species. A tiny machine, built by human hands in the 1970s, had now carried our curiosity across the ultimate threshold, a silent ambassador drifting in the cosmic ocean. Just as the boundary seemed near, Voyager 1 entered a bizarre region unlike any predicted. Scientists called it the magnetic highway, a cosmic freeway where the rules of particle travel were rewritten. For months, the probe drifted through this zone, its instruments recording a dramatic and continuous exchange. Magnetic field lines from the sun, which had long guided the flow of solar particles, were now connecting directly with magnetic lines from the galaxy beyond. This unexpected connection opened a channel, a two-way street for cosmic material. Low-energy charged particles that had been trapped inside our solar bubble suddenly found an exit ramp, streaming outward into the void. Simultaneously, high-energy cosmic rays from interstellar space, which had been largely blocked, now found an open on-ramp flooding inward toward the probe. This was not the simple, sharp boundary many had envisioned. It was a messy, dynamic, and layered interface, a place of complex magnetic handshakes between our star and the galaxy. The magnetic highway forced a complete revision of our models. The edge of the solar system was not a wall, but a porous and active membrane, a region with its own unique and turbulent physics. This surprising discovery revealed that the sun's influence does not simply stop. It gradually and chaotically dissipates in a final, intricate dance with the interstellar wind. The data that trickled back was our first true taste of the galaxy. Voyager 1 had crossed the ultimate threshold, and its aging instruments were now sampling the pristine interstellar medium, the raw material between the stars. The readings immediately upended expectations. The galactic magnetic field, the invisible scaffold of our local galactic neighborhood, was far stronger than any model had predicted, and it was aligned in a direction nobody had foreseen. Our solar system was sailing through a powerful and structured magnetic sea, a fundamental discovery that reshaped our understanding of the local cosmic environment. Then there was the hum. Voyager 1's plasma wave instrument detected a faint, persistent oscillation, a low-frequency vibration in the ionized gas of the interstellar medium. This gentle, constant ringing is the signature of a quiet, tenuous plasma, the baseline murmur of the galaxy itself. It is the sound of near silence, the ambient noise of the void. Perhaps the most surprising find was a faint but persistent leak. Even from outside the Heliosphere, the probe detected traces of solar material, atoms that had once been part of the solar wind, now drifting free into the galactic expanse. The Sun's bubble is not a perfect seal. It is a porous membrane, allowing some of its essence to slowly bleed out into the cosmos. This priceless data provides a singular baseline, a detailed characterization of the specific interstellar cloud our solar system is currently moving through. Voyager 1 is not just a traveler, it is a weather station reporting back from a foreign shore, giving us our first real understanding of the ocean our entire solar system is floating in. 6 years after its twin, Voyager 2 finally slipped across the same invisible boundary. Its later arrival in 2018 was not a simple repeat of history, it was a crucial upgrade to our vision. While Voyager 1 had lost its plasma science instrument decades before its crossing, Voyager 2's was still perfectly functional. This single working sensor was the key to unlocking the true nature of the space outside. For the first time, we could directly measure the density and temperature of the interstellar plasma itself, the actual substance of the galactic ocean. The confirmation was stunning. Voyager 2's readings largely matched what its twin had inferred, proving that Voyager 1's singular data point was not an anomaly. We were truly outside, but the story did not end with simple confirmation. The two probes also recorded subtle yet significant differences in the conditions at the boundary. The heliopause was not a static wall, identical in all places. It was a dynamic and shifting frontier, one that could change over time and depending on where you crossed it. Having two data points from different parts of the sky was like suddenly gaining depth perception after seeing in only 2 dimensions. This stereoscopic view allowed scientists to map the contours of our solar bubble in a way that was previously impossible. The corroboration from Voyager 2 transformed a lone, astonishing measurement into a robust scientific truth, solidifying our understanding of how the Sun's influence finally yields to the immense pressures of the galaxy. The faint electrical heartbeat of each Voyager is a testament to endurance itself. Those nuclear batteries, the RTGs, are not like a power outlet you can simply plug into. They are slowly and irrevocably fading. Each year, they produce about 4 fewer watts of electricity, a relentless decline that has forced the ground team into a state of careful, calculated triage. They are the remote doctors for a patient over 15 billion miles away, making decisions that can never be undone. To keep the core scientific instruments alive, they have had to sacrifice other systems. One by one, the heaters that once kept vital components warm have been shut down, condemning those parts to the unforgiving cold of deep space. Non-essential systems, once critical for the planetary flybys, have been powered off forever. The team has even developed ingenious software patches, clever workarounds that allow the probes to share power between different systems, a kind of energy budgeting on an interstellar scale. Every choice is a high-stakes gamble. Should they keep a plasma sensor running or a cosmic ray detector? Which data stream is more precious when the power for both is running out? This is not merely a technical challenge. It is a profound exercise in prioritization, a race against a silent clock to extract every last whisper of discovery from these aging pioneers before the final signal winks out. That faint whisper of data is a miracle of engineering in its own right. The signals we send and receive now travel for more than 21 hours just to reach Voyager 1, a one-way conversation where every question and answer takes nearly 2 full days. By the time its whisper, traveling at the immutable speed of light, finally washes over Earth, the power of that signal is almost unimaginably weak. It is over 20 billion times fainter than the power emitted by a standard digital watch battery. To hear such a faint call from the void requires an ear of extraordinary sensitivity. That ear is NAS, a deep space network, a global array of gigantic radio antennas with the most sensitive dishes measuring 70 meters across. These colossal white bowls, pointed with exquisite precision, spend hours each day listening for that one specific whisper amid the cosmic static. They are not just listening, they are also shouting. The commands we send from Earth are blasted toward the probes with enough power to punch through the background noise. A message in a bottle thrown with incredible force toward a microscopic target billions of miles away. But the conversation has slowed to a glacial pace. The data rate from Voyager has dwindled to a mere 160 bits per second, a slow trickle of information. To put that in perspective, during its flyby of Jupiter, the probe could send data at 21,000 bits per second. Today, it would take almost 2 full days to transmit a single, average-quality photograph, which is precisely why the cameras were turned off long ago. Every precious bit of data now is reserved for the fundamental readings of the interstellar environment, the measurements of cosmic rays and magnetic fields that are the mission's final scientific legacy. This painstaking, slow-motion dialogue across the greatest distance humanity has ever bridged is a profound testament to our persistence, a declaration that even a whisper from the edge of nothing is worth straining to hear. Their trajectories now carry them into a future almost beyond our comprehension. These spacecraft are not aimed at any specific star. They are simply continuing on the path set by their final planetary encounters, drifting on an eternal journey through the Milky Way. Voyager 1 sails toward the constellation Audacious, and in about 40,000 years, it will make its closest approach to any celestial body, passing within 1.6 light-years of a dim red dwarf star known as Gliese 445. Its twin, Voyager 2, is bound for the constellations of Sagittarius and Pavo, and on a similar timescale of roughly 40,000 years, it will drift within 1.7 light-years of the star Ross 248. To call these events close encounters is a cosmic misnomer. These distances are immense, far wider than the gap between our Sun and its nearest stellar neighbor. They are simply two travelers crossing a vast and empty street, unaware of the houses on either side. Their escape velocities are staggering by human standards, over 35,000 miles per hour, a speed that would circle the Earth in under 45 minutes. Yet within the galaxy, this pace is achingly slow, a leisurely stroll across a continent. It would take Voyager 1 nearly 1.5 billion years to complete a single orbit around the galactic center. Their ultimate destiny is not a destination but the journey itself. They will wander the spiral arms of the Milky Way for eons, long after their nuclear hearts have grown cold and their final transmissions have ceased. They will become silent, inert monuments to a species that once looked up and wondered, drifting through the darkness long after human civilization on Earth has transformed into something unrecognizable. They carry the golden record not as an active message, but as a fossil, a testament to a moment in time when humanity reached beyond its cradle and cast a piece of itself into the cosmic ocean, forever adrift. That hopeful gesture cast into the cosmic ocean forces a profound and uncomfortable question upon us. What single story would you choose to tell about our entire species? The team behind the golden record had to answer this, and their choices reveal as much about our aspirations as our reality. They included the sounds of a heartbeat and a mother's kiss, alongside the roar of a Saturn V rocket. They captured the music of Mozart and the blues of Blind Willie Johnson. There are images of a supermarket full of abundance and a photograph of a traffic jam in Thailand, hinting at our complex social structures and their frustrations. This was a deliberate choice to present the whole human experience, not an idealized brochure. It showcases our capacity for great art and tenderness, but also our struggles with organization and perhaps even our own numbers. The record is therefore a philosophical Rorschach test. It asks us to look at this collection of sounds and sights and decide for ourselves what it says about humanity's soul. Is it a testament to our creative spirit and resilience, or a document of a species grappling with its own success? This duality makes the record a time capsule for us, the people of Earth, just as much as for any distant intelligence. It is a mirror held up to who we were in the late 20th century, a snapshot of our fears and our highest hopes frozen in gold and copper. That lonely message, now traveling in the void, is a permanent symbol of a fundamental human need, the desire to call out and say we are here, and to hope that somewhere someone is listening. The Voyagers were built for a 4-year mission, a brief sprint to Jupiter and Saturn. The fact that they are still talking to us 45 years later from the space between the stars defies all expectation. This is not just longevity, it is a sustained defiance of the void, an engineering miracle born from a perfect storm of foresight and robust design. Every component was built with a level of quality and redundancy that seems almost alien in our modern era of planned obsolescence. The crafts were hardened against the brutal radiation of Jupiter's belts, shielded from the constant peppering of micrometeoroids, and constructed to endure a cold that steadily drains the very life from their systems. Their resilience is a direct result of the painstaking craftsmanship of the 1970s, a time when every circuit was tested and every connection was made to last. This incredible durability has gifted science with an unparalleled windfall. A mission planned for a few years has delivered nearly 5 decades of continuous discovery, transforming a planetary tour into humanity's first direct exploration of the galactic ocean. It stands as a quiet, persistent proof of what we can accomplish when we build not just for the immediate goal, but for a future we can barely imagine. The legacy of these 2 spacecraft is etched not just in textbooks, but in the very questions that now guide our exploration. Before Voyager, the outer planets were distant points of light, their moons simple specks. The probes transformed these abstract worlds into dynamic, individual characters, each with its own complex story. They gave us the first evidence of active geology beyond Earth, with Iowa's fiery plumes rewriting the rules for where we might find volcanic activity. They revealed that ring systems were not simple, solid hoops but intricate disks of countless particles, a celestial ballet governed by the subtle gravity of shepherd moons. They introduced us to Triton's cryovolcanoes and Neptune's supersonic winds, proving that distance from the sun does not mean a world is dead. This torrent of new data fundamentally reshaped the entire field of planetary science. The detailed images and readings from Jupiter and Saturn provided the essential roadmaps for the Galileo and Cassini missions, which later orbited those giants for years, diving deeper into the mysteries Voyager first spotted. Cassini's long study of Enceladus, for instance, was a direct result of Voyager's tantalizing clue that its surface was strangely smooth and young. The discovery of Uranian and Neptunian magnetic fields, bizarrely offset and powerful, forced scientists to completely rethink how planetary magnetic dynamos can operate in the unique interior of an ice giant. Perhaps most remarkably, the Voyager Data Archive is a gift that keeps on giving. Scientists today, armed with modern computers and new analytical techniques, still comb through the old datasets, uncovering subtle signals and patterns that were invisible 40 years ago. They might find a faint new ringlet in the Saturnian data, or reinterpret a magnetic field reading to reveal a new aspect of the solar wind. The mission's true legacy, therefore, is a dual one. It provided a flood of definitive answers, but more importantly, it raised a whole new generation of profound questions, setting a course for discovery that we are still following today. Behind every command sent across the void was a room full of people on Earth. The Voyagers were not autonomous robots, they were extensions of a human team, a collective intelligence guiding them from the calm of a control room. This mission required thousands of individuals, from the engineers who hand-soldered circuits in the 1970s to the flight controllers who, decades later, learned to diagnose problems on a machine older than they were. Many dedicated their entire professional lives to these two spacecraft, growing up alongside them, their own careers mirroring the probe's epic journey. They developed an almost familial intuition for the Voyager's personalities, learning every subtle quirk in their data streams, every minor anomaly that signaled a potential issue. They knew the sound of a healthy signal and the worrying silence of a glitch. This deep, intimate knowledge was their most powerful tool. When a thruster fired a millisecond too long or a data format suddenly changed, these specialists did not just consult a manual, they listened, they interpreted, they understood. Their work became a delicate ballet of remote command and diagnosis, a slow, thoughtful dance where every move was considered, tested, and then sent on a 20-hour journey. This was not a job of frantic urgency, but one of profound patience and meticulous care, a commitment measured not in weeks but in decades. The spacecraft's longevity is a direct reflection of this human dedication, a testament to the passion and problem-solving of the people who refused to let their creations fade into silence. That final portrait of our world came from a quiet request in the mission's later years. After its primary mission was complete, the astronomer Carl Sagan pleaded with NASA to command Voyager 1 to turn its cameras homeward for one last look. From a staggering distance of 3.7 billion miles, the spacecraft captured a series of 60 images, creating a family portrait of our solar system. In one of those frames, Earth appears not as a vibrant marble of blue and white, but as a tiny, pale blue speck, almost lost in the vastness. It is suspended within a scattered sunbeam, a mote of dust floating in an infinite dark room. There is no hint of national borders, no sign of our sprawling cities or our great engineering works. All of human history, every triumph and every tragedy, every person who has ever lived played out on that single, faint pixel of light. Sagan's reflection on this image transformed it from a simple photograph into a profound philosophical statement. He saw it as a demonstration of our planet's heartbreaking fragility and our utter cosmic isolation. In the grand arena of the universe, our world is just a lonely outpost, a solitary haven for life as we know it, adrift in an unimaginable void. This perspective forces a humbling realization. All our conflicts, all our divisions, all our pride exist on that one tiny stage. The pale blue dot asks us to see beyond our tribal boundaries and recognize the fundamental unity of the human experiment. It is a silent plea from the cosmos itself, reminding us that we have only one home, one delicate world to cherish and protect. This single image, a gift from a machine at the edge of nothing, may be Voyager's most important discovery of all, a timeless lesson in humility sent back from the void. Those plasma wave instruments gave the void a voice. They translate the faint, rhythmic vibrations of charged particles in space into sounds our ears can understand, turning abstract data into an eerie cosmic symphony. Crossing the heliopause was not a silent event. It was marked by a dramatic crescendo, a sharp spike of plasma wave activity that sounded like a sudden, violent thunderclap in the emptiness. This was the sonic signature of a historic collision, the moment our solar bubble met the interstellar wind. But after that initial shock faded, the instruments picked up something far more subtle and enduring, a persistent, low-frequency hum. This is the baseline murmur of the galaxy itself, the gentle, continuous oscillation of plasma in the local interstellar medium. It is not the sound of nothing, but the sound of near nothing, a tenuous sea of ionized gas vibrating with a quiet, innate energy. This hum provides an intuitive glimpse into an otherwise invisible realm. We cannot see this plasma with our eyes, but through these recordings, we can hear its presence, a constant, whispering proof that the space between stars is alive with subtle motion. These sounds transform our perception of the cosmos from a cold, empty blackness into a dynamic and resonant medium. They are a haunting and beautiful reminder that even in the deepest quiet of interstellar space, there is a fundamental vibration, a symphony of energy playing on a scale almost beyond human comprehension. That slow fade of power dictates the mission's final chapter. The electrical heartbeat of each Voyager is growing fainter every year, a quiet countdown to an inevitable silence. Engineers on Earth are now performing a delicate and heartbreaking triage, carefully deciding which of the last few functioning systems must be sacrificed next to keep the others alive. The heaters were the first to go, surrendering components to the brutal cold of space. Soon, the choice will come down to the scientific instruments themselves. Which is more precious, the cosmic ray detector or the plasma wave sensor? This is not a failure, but the final, planned phase of an unimaginably long life. Current estimates suggest that by around 2030, there will simply not be enough power left to run even a single instrument. The final act will be a quiet command sent across a 22-hour light travel time to permanently shut down the last remaining scientific tool. After that, the Voyagers will not be dead, but they will fall silent. They will become inert monuments, flying tombs carrying their golden cargo. Their mission will transform in that instant from one of active discovery to one of passive endurance. They will no longer speak to us, but they will forever carry our message forward. This final shutdown will be a profoundly poignant moment for the team that has nurtured them for decades, a symbolic end to direct contact. Yet it is also a celebration of a triumph that has shattered every expectation, a mission that began with a 4-year plan and gifted us nearly 6 decades of revelation, forever expanding our understanding of both our cosmic neighborhood and our own potential to reach into the unknown. Voyager's story has long escaped the confines of scientific journals to become something more, a shared cultural touchstone for our entire species. It is a narrative that has ignited a fire of curiosity in generations of young minds. For decades, students have looked up at the night sky, learned of a tiny spacecraft sailing among the stars, and felt a calling. That calling has guided countless individuals into careers as scientists, engineers, and mathematicians, a direct legacy of the mission's audacious spirit. Its influence echoes through our media, from the soaring scores of documentary soundtracks to the pages of popular science books that frame its journey as the ultimate human adventure. This cultural resonance stems from a powerful and unifying idea that humanity, at its best, can set aside terrestrial divisions to achieve something magnificent and peaceful. The sight of international scientists working together in a control room is as much a part of the Voyager legacy as the data it sends back. These 2 small probes have become a symbol of our collective potential, a physical manifestation of our innate desire to push beyond the horizon. The profound simplicity of their mission, to journey into the absolute unknown, taps into a deep and ancient part of the human spirit. It is the same impulse that drove the first sailors to cross uncharted oceans and the first astronomers to map the heavens. Voyager carries that legacy forward, a silent promise that our curiosity can carry us further than we ever dreamed, ensuring its story will not just be remembered, but will continue to spark wonder for centuries to come. The Voyagers are not just explorers, they are scouts. Every bit of data they have sent back from the void is a lesson for the next generation of interstellar travelers. Their decades-long journey has provided the first ever engineering report from the space between stars, a priceless document detailing how to survive out there. We now know the true radiation environment beyond the sun's protection, the density of microscopic dust grains that could sandblast a probe's hull over millennia, and the complex behavior of interstellar plasma. These are not abstract readings, they are the specifications for building a tougher, more resilient spacecraft. The need for robust, long-lived power is clearer than ever. Future probes will require advanced versions of the nuclear batteries that have kept the Voyagers alive, or perhaps entirely new power sources capable of functioning for centuries. Their legacy also underscores the absolute necessity of autonomy. A probe decades away from Earth cannot wait for human instructions when a critical maneuver is needed. It must be able to think for itself, to diagnose problems and implement solutions in real time. This is the foundation for missions now on the drawing board, like NAS, a concept for an interstellar probe. This ambitious mission aims to launch around 2036, designed from the start to travel faster and venture even deeper into the galactic ocean than the Voyagers could ever reach. It would carry instruments specifically designed to study the invisible matter and forces that shape our galactic neighborhood, tools born directly from the questions Voyager first raised. The Pathfinders have shown us that the gulf between stars is not an impassable barrier, but a new ocean waiting for our ships. They have handed us the first, crucial pages of the roadmap, proving that humanity's next great leap into the galaxy is not a fantasy, but a tangible, achievable goal. One day, the silence will arrive not with a bang, but with a quiet absence. The steady carrier wave, that faint electronic heartbeat from the void, will simply vanish from the screens at the deep space network. The last transmission will not be a dramatic final message, but a simple, irreversible drop in voltage, a final sigh as the last of the plutonium's decaying heat fails to generate enough electricity to power the transmitter. For a time, the giant antennas will remain pointed at the predicted coordinates, listening intently for a signal that might miraculously return, a habit born of decades of vigilance. But the silence will hold. Eventually, the mission managers will make the official declaration. The project will be formally closed, and the final terabytes of data will be sealed into the archives, a complete record of an epic conversation. There will undoubtedly be a profound sadness in that moment, a personal sense of loss for the engineers who have spent their careers shepherding these distant travelers. Yet, this sadness will be inextricably woven with a deep and overwhelming pride. The mission was designed for 4 years, it was given 45, and it returned a treasure that redefined our solar system and gave us our first taste of interstellar space. The end of the signal is not a failure, it is the completion of an unprecedented scientific gift. From that moment on, the Voyagers transform. They shed their roles as active explorers and become something new, something eternal. They are silent couriers now, their golden records intact, their metal bodies slowly cooling to the background temperature of the universe. They will continue on their set trajectories, no longer speaking to us, but forever carrying a piece of us forward into the galactic future. Long after our cities have turned to dust and human civilization has evolved into unrecognizable forms, these two artifacts will still be sailing through the starry dark, a permanent part of the Milky Way, a testament to a species on a small blue world who once dared to send its name into the endless night. The journey of the Voyager spacecraft stands as one of humanity's greatest adventures, a breathtaking chronicle of ingenuity, perseverance, and an insatiable thirst for knowledge. These two small probes did far more than just complete a checklist of scientific objectives. They became our eyes and ears in the dark, fundamentally redefining our understanding of the cosmos. They transformed the gas giants from pinpricks of light into dynamic, storm-racked worlds with families of bizarre and active moons. They mapped the invisible architecture of the sun's protective bubble and then boldly sailed through its final boundary, giving us our first direct taste of the galactic ocean. The data they sent back was not just numbers on a screen. It was the first chapter in a new story, the story of our solar system's place within the wider galaxy. But their impact transcends pure science. The Voyagers are more than just sophisticated machines. They are profound symbols of hope and exploration. They represent a species courageous enough to cast a message in a bottle into the cosmic sea, carrying a fragile piece of our collective identity into the vast community of the Milky Way. As their electrical heartbeat grows fainter with each passing year, their legacy does not dim, it burns ever brighter, a permanent flame ignited in the void. They remind us that our curiosity is our greatest compass, urging us to forever look up, to ask the next question, and to continue our eternal venture into the unknown.